Hi everyone, welcome to today's video. Today we are going to learn about lazy binding. But before that, towards your left, you can see a terminal where I have a beautiful yet very small program hello.c, which is doing nothing but calling the puts function, which belongs to uh, dynamic library libc with the formatted string hello lazy binding, nothing else. Today we are going to see this executable which I've already compiled using gcc, and we'll use that for demonstration. Towards your right, this picture belongs to a beautiful book called Practical Binary Analysis. And this is a snippet of the flow diagram, how exactly step by step lazy binding happens. We'll come to it in a bit. Before that, let's define lazy binding. So when an ELF binary is loaded into memory for execution, it often depends on shared libraries. However, at compile time, the exact memory addresses of shared library functions are unknown. Instead of resolving all the function addresses immediately, Linux defers resolution until the first time a function is actually called. This process is known as lazy binding. Lazy binding improves performance by avoiding unnecessary work at startup. If a program never calls a particular shared function, the system does not waste time resolving it. Thus, only when a function is actually used during the dynamic linker resolves its address and store it in the memory, and this whole process is called lazy binding. We bind an external function only when it is actually needed. Now, before going for the actual lazy binding process, I would like to describe two sections within the binary. Uh, One is called PLT or procedure linkage table, and the other one is called GOT or global offset table. So, in the picture towards your right, you can see that this is basically the whole code section of the binary. Within that, it is showing some kind of PLT section or procedure linkage table. Now, this is the text section, which is basically main code of the binary, and there are other section also mentioned at got.plt. So procedure linkage table, basically this section contains stub that handle function calls to shared libraries. Instead of directly storing the function addresses, PLT redirects function call dynamically. Again, global offset table, this section holds the resolved addresses of shared library functions. When a function is first called, its address is not yet available, so the dynamic linker basically updates this address. Right. There are multiple GOT sections. There is a section called GOT, which basically holds addresses of global data variable. And there is another section called got.plt, which holds the addresses of shared library function resolved via the PLT. Right. So let's look at how a PLT stub actually looks like in assembly. Right. So for that, we'll use our hello program, and we can use this particular instruction with object done, and then we can drop the PLT section in the disassemble hello code. So if we do that, you can see the disassembly of the whole PLT section. This is more or less same for this particular file format, x86 architecture. So within the PLT section, you will get multiple function calls which belongs to the external function, and we are more specifically interested into this puts.plt. So you can see here also towards your right there is this puts.plt, uh, which is jumping to some place, and then you have push and some particular number. Here it's push and 8, and then it is here in this code it is jumping to default stub, and here it is jumping to init and 30 with the offset. So basically, if you go to the init, this hex 30 offset, we have a default stub basically, which is doing nothing but again pushing some variable to the stack and then indirectly jumping somewhere. Right. So now we know that every PLT section has some kind of format. It has a default stub and then, an entry for each function address. Before going to that, I would also like to show how GOT actually looks like, or got.plt looks like. So for that, I am going to use this interface called Ghidra. For this particular binary, we only have the GOT section. So I am showing you the GOT section. You can see in the GOT section, all they have is some kind of reference to some function address. For example, we are looking into this particular puts function, and then there is an address variable. So in the beginning, this address variable is not actually set to the original external puts function address, but after the lazy binding, this address will be actually modified with the puts function call address. Okay. Now we have looked into the PLT section, the GOT section, the text section, and then now let's try to see how lazy binding is actually happening. So let's see in your hello.c function in the main code, whenever, maybe let me try to see that. Let's disassemble our hello program. If we do that, we have the whole disassemble code, and particularly here within the main function, this particular call to puts.plt is actually happening. So first you start from the main function, then you call this puts.plt, and then it goes to the PLT section. Within the puts.plt section, it basically indirectly jumps first toward the GOT section or got.plt. Now, for the first time, this address is basically nothing but the second instruction address after the jump, which is nothing but put 0. So once we are at the got.plt for the first time, then again we came back to the next instruction. We push the 0 to the stack, and then we jump to the default stub. Within the default stub, as you can already see, first we also again put something on the stack, then we indirectly jump some point. For the first time, this fifth step is basically we are directing to dynamic linker. Now the dynamic linker knows that you need an address of the actual puts function. So it dynamically resolve those addresses and then update the got.plt with the actual puts function address. And then it calls the put function in the sixth step. This is a one-time process. Once this particular address is actually modified with the puts function address, second time whenever you call the puts function, so basically it goes to the GOT, and from the GOT it fetches the address of the put function, and then it directly runs the put function. So every time a new external function is getting called, basically dynamic linker goes through this lazy binding process and sets up the address for it. Now there can be a very important question that one might ask: while the PLT doesn't store function address directly, instead relies on the GOT, right? So what if we directly update this puts function address in this indirect jump of the puts.plt? Then we don't have to go through this all of this indirect process, right? Um, but there are multiple reasons why we don't do that. First is security. So usually these code pages, that is PLT or text section, are basically not writable, because if they are writable, an attacker could modify it and inject malicious code, right? So thus we use GOT. Basically, GOT being a data section, is it can be writable while keeping the code section read only. So from the attack model point of view, modifying GOT has a weaker effect than modifying the PLT, and that is why we do that. And the second reason is basically shared library mapping. So, as we know that basically we have only one copy of the physically loaded dynamic libraries, and dynamic linkers map this physical address to multiple virtual address of multiple process, and as each process has its own GOT, this mapping makes sure that the program doesn't crash and it effectively can execute these external functions. And the third is obviously efficiency. Since each GOT entry stores the resolve function address, subsequent calls can skip the PLT and directly access the function, improving the execution speed. Still, even with this writable GOT, there can be security concerns. For example, while lazy binding improves performance, it introduces security vulnerabilities, primarily GOT overwrite attacks. Since GOT is writable, an attacker can obviously modify this function address itself and it may redirect to some malicious code. Right. So this is again not expectable. And that is why there is this RELRO enable. So it's basically a technique. Whenever you are done with this kind of lazy binding, you make the GOT read only again so that no one can tamper with it. In conclusion, lazy binding optimizes function resolution by deferring address lookups until they are actually needed. This is done using PLT as well as GOT, where the GOT holds function addresses and updates them dynamically. However, lazy binding comes with security risks such as GOT override attacks and which can be mitigated using RELRO. And understanding this mechanism is crucial for both performance optimization as well as security defenses in ELF binary. This concludes our discussion on lazy binding, PLT, and GOT today. In the next part, we'll demonstrate this process step by step using real ELF binaries, JDB, and Objectum. Thank you so much.